unconditional jump. The JMP or jump instruction allows to set the value of EIP. It looks like this. Jump destination. It has only one argument. This instruction actually jumps to a different location in the program to execute different code. It means that it goes to somewhere else and then the execution of the program is going to continue from this new location. Examples. Jump ECX. This instruction changes EIP to the contents of ECX. It means that the execution will continue from the address ECX. In a different formulation, it changes the value of EIP to the value of ECX. Another example. Jump and then this base 16 number, this long number. This instruction changes EIP to this new value, some arbitrary location in memory. The program will continue execution on that address. In a bit of a different formulation, we assign this number inside EIP. The jump instruction is actually some kind of an indirect way to change the value of EIP. We can put some value inside EIP, but only using this kind of instruction, the jump instruction. It's like a special case of the move instruction, which only works for the EIP register. You can think about it that way, for example. Let's talk about labels. When writing our programs, you usually can't predict the loading location in memory. What am I actually talking about here? You write your program inside your editor and it's not running yet, it's only text. While writing your program, usually you cannot predict the location in memory that it will stay in. Generally speaking, you are not supposed to know the location in memory where your program is going to be loaded. This is mostly important when you write assembly programs that are going to work over some kind of operation system. For example, if you write your program so that they run inside the Windows operation system or maybe in the Linux operation system, then definitely you are not going to choose your own location in memory. Labels are a way of referring to a location in our program without knowing the exact address of that location at runtime. What does that mean? Let's look at an example. We have here the first instruction, move ECX 0, which 0 is ECX. And now we have this strange thing, which is not actually an instruction. This is a label. You can write this kind of label in your own code when using FASM, and actually most of the assemblers these days for x86 architecture, they have support for this kind of construct, which is called a label. Now, let's continue to read the code. The next instruction is inc ECX, which increases ECX. And the next one is jump, and the argument is my label. You might be a bit surprised here because I earlier said that jump can only receive things like registers or maybe constants, like the large number that we have seen before. Let us see it again. Here we have, for example, ECX or maybe a large number, but what is this my label given as an argument to jump? Well, there is an explanation. At the time of writing the program, you don't want to deal with memory location and large numbers. You don't want to do this. You want to think about the actual logic of the program and not deal with the simple specifics and trivialities of choosing locations in memory and things like that. So you tell the assembler about the location that you want to refer to. You actually want to jump to this instruction. This is what this code is trying to do. It invokes this instruction, inc ECX, and then it jumps back to this instruction, to inc. Actually, it is going to be some kind of a loop. But what is going to actually happen? The assembler is going to read this code, and then it is going to translate it. the assembler is going to replace this my label with the actual address of the inc instruction. Let's look further at this example. This is the code that we write inside our text editor before the assembly process. Now let's imagine that this code is loaded to memory before the execution of the program begins. Here we have some kind of addresses that this program resides in. If you have never seen something like this, like addresses inside the memory, don't be scared. We are going to speak about it in a much more detailed manner in the future. However, for now, just believe me that your code is going to be loaded somewhere in memory. So we have those three instructions. We can see from the actual addresses that we can actually guess the sizes of the opcodes. For example, this instruction, move ECX 0, we can see that it has size of 5 bytes because the next instruction begins from this address and the difference between those two addresses is 5. We can actually also guess that the increase instruction is of size 1 because the next address here ends with 6 and the difference between those two addresses is just 1. So we can know the size of the move instructions, which is 5, and the inc instruction, which is 1. However, we cannot infer from this formulation of addresses the size of the jump instruction. But this is just an example of things that we can infer from what we see here. You can also see that my label is not going to take any place in memory because it is not a real thing. The processor is not going to see this label. It is just some kind of hint for the assembler, so he can help you do what you want. Instead of my label here, the assembler is going to replace it with something else. It is just going to be replaced with the actual address of this instruction, of the increase instruction. Maybe you have missed it, so let me show you again. This is what you have in your code, in your text editor before the assembly process, and that's what happens after the assembler goes over your code. Actually, the assembler is also going to translate all your instructions into their final encoding, but thinking about it, or only about the labels are going to be translated about this way. The label is just replaced with the actual address of the instruction that it points to. I hope that it is clear. Now let's try to understand what is going to happen in this code. Let's assume that ECX has some initial value that we don't know about. We are going to mark it with question marks. Also in the beginning, EIP is going to point at this address, 4F1 and 30, which is this address. Usually we are going to mark the location of the current execution with this kind of arrow, which marks the contents of EIP, because the contents of EIP is this address. That's what we mean when we say that EIP is the instruction pointer, because it points, like this arrow, on the current instruction. Let's move on. We can see that EIP has changed. It has increased by 5, which is the size of this instruction, the move instruction. And also ECX has changed to 0, and this is pretty much expected. We already know that the move instruction is going to move 0 inside ECX. The next instruction is increase. It is going to increase ECX by 1, and we expect EIP to move to the next instruction. And as expected, that's exactly what happened. ECX is now 1, and EIP now points to the jump instruction. The jump instruction is a special instruction. Now we expect that it is going to change EIP to this number, 4F1005, which is going to be the previous instruction, inc. And we get what we expected. We can move on a bit and see what happens. Maybe you have already guessed, we have here some kind of infinite loop. That is because there is no real way of exiting this kind of loop. This is a loop because jump is always going to jump back to this instruction, increase ECX. And increase ECX is always followed by this instruction, jump. So the processor has no way of getting out of this loop. It can execute it infinitely until you ask him to stop. Processors can actually do that. They can actually run indefinitely until you tell them to stop. If your program is not very smart, things like this can happen to you. This is called infinite loop. Jump. Continued. It is the job of the assembler to translate labels into actual addresses. The jump instruction looks like a simple instruction. However, it has few different encoding versions. For example, absolute jump. This kind of jump jumps to a specified location in memory. The other kind of jump is called relative jump. This one jumps to a location which is, for example, X bytes from this location. So the first jump is absolute because it just jumps to a specific location, an absolute location. And relative jump is going to jump to different places according to the current location. So you can have the same jump instruction, the same relative jump instruction in two different places in your code, and in those two different places the jump instruction is going to change EIP to different numbers because it is a relative jump. Most of the time the assembler is going to pick the suitable version for you. So for now you don't have to worry about it. Maybe in the future you are going to choose it yourself if you really want to, or you have a special preference in some special case, but usually you don't have to worry about it. You just write down JMP and the assembler is going to pick the right one for you. Usually if it's very close, it is very probable that the assembler is going to pick the relative jump. That is because the relative jump is usually shorter. I simplified things a bit here. There are even more kinds of jumps, but they all hide inside this generic JMP instruction, which contains all of them. And the assembler usually just picks the right one. I think there are actually maybe even 3 or 4 types. You can check it out yourself in the future. Jump allows to change EIP unconditionally. We would like also to change EIP conditionally, maybe based on some previous value that we have obtained. But how could we do that? That is something that we are going to learn in the future lectures. We are going to learn how to branch our code according to the result of the last calculation. So let's summarize. So far we created only linear programs. We used our computer like a pocket calculator, which doesn't really give us much power as programmers, at least not as we would like to. The JMP instructions allows us to branch unconditionally. We created a simple loop to demonstrate it. We will later learn how to branch conditionally. Branch according to the result of the last calculation. See you next time.